Hello class, welcome to our lesson today dealing with section 8.2. Section 8.2 is the beginning of what's known as hypothesis testing. You can kind of think of this as more of a scientific method type approach to statistics. So there's going to be kind of a routine to everything. There's going to be a lot of information here today on our lesson and our video. You want to make sure you have the basic ideas of what hypothesis testing is really talking about, what the reaction needs to be, what my conclusions need to be, and how to find some things such as p-values and critical values as we move through today. Okay, hypothesis testing is basically taking a claim about something about the population, some piece of it or some property or a situation of that population. And then we're going to either be looking at a proportion, a mean, or a standard deviation, and that's what will be tested. For our class purposes, we'll probably focus a lot on the mean and the proportion ideas, probably not so much on the standard deviation as we go through our hypothesis testing for our class. What we're basically doing is taking an event that we think is unusual or what's known as a rare event, and then basically putting some backbone to it and saying this is why I think of this statistically is a rare event. So, for example, if I toss a coin and get 95 tails, your immediate reaction is probably, well, that coin's not fair or something's happening with this situation. Whenever we have that reaction, it probably is a good indicator that there's going to be something unusual happening, and we just are going to be able to try to find that as we go through those situations. What we don't want to say is, well, it seems unusual, so I'm going to say it's unusual. There should be something else that we're looking at in order to figure out what those what is unusual or what would be considered a rare event. All right. Hypothesis tests have two pieces. The first is what's known as the null hypothesis, which is always denoted H sub 0. This is a statement that's based on the parameter, so like where our focus is on the population proportion or mean, and it's always equal to some claimed value. So like this first one would be the proportion, my null hypothesis is the proportion equals 0.5, or the mean equals 14.5. Then we're going to test the null hypothesis against an alternative. And our conclusion is either going to reject or fail to reject whatever we're trying to show. We never prove something necessarily. We always reject or fail to reject whatever's given to us in the null hypothesis. The alternative hypothesis is either denoted H sub 1 or H sub A. I probably tend to do more H sub A just for alternative hypothesis. And this is what we're showing, something differs from whatever's given to us. Now, this will make kind of sense maybe later on, but it should always be either less than, greater than, or not equal to as an alternative hypothesis. So here my alternative would be the proportion is less than 0.5, the proportion is greater than 0.5, or the proportion is not equal to 0.5. This is just an example. It doesn't always have to be 0.5, but just realize that the alternative hypothesis should either be a less than, greater than, or not equal to based upon the information that we're looking at and trying to claim. There are three types of hypothesis testing then. There's a two-tailed test, which is if it's a not equal to. Okay, if it's a not equal to alternative hypothesis, it's going to have two sides, and you can kind of think of that's similar to the confidence interval idea. There's a left-tailed test, which would be anytime it's a less than, because less than would be area to the left. And then anytime it's greater than would be an area to the right. So our goal is to make things look like things that we've seen before with probability and z-tables and t-tables to make a two-sided or a one-sided test. This also explains maybe on the t-table why it says a line that has one-sided test and a line that says two-sided test. And we'll use that hopefully to find some answers later on in our chapter. All right, so the claim here is that people from age 19 to 25 who own a house is equal to 15%. My claim is something about 15%. My null hypothesis is always equal to, so P equals the 0.15. The alternative, if I just want to show if it's equal to 15%, the alternative is not equal to. So my alternative hypothesis would be P does not equal 15%. And again, this will come more naturally as we keep looking at more questions. We're just getting a start with some of these ideas in section 2 of chapter 8. The next one says the mean weight of airline passengers is more than 195. So my null hypothesis is it equals 195. Now, depending on the situation, it's a little tricky. I don't want to confuse anyone right now. So we're going to go under the assumption that I wanted to test to see if it was in fact over 195. So then my mean is greater than 195. You'll also notice that the last slide used P equals for proportion or probability. This one is mu equals, or the mean, because it's an average type question, not a proportion question like this previous one was. The next question is dealing with majority. Now, majority shows up a decent amount of time. So our claim is that a majority of people would have a credit card. My null hypothesis would be it's 50-50, half don't, half do. And then the alternative would be the proportion is greater than 50% or 0.5. When you're looking at these situations, the important thing about the claim and the null hypothesis and the alternative is that the null hypothesis should always have the equal to, and the alternative should have less than, greater than, or not equal to, depending on the situation. There's 3 formulas to find test statistics. If it's a proportion question, it has to be this version. Notice it has p hat, that's the proportion of the sample, minus the population proportion, and then square root of p, q, and then divide by n, the sample size. For means, you have to pay a little bit more attention. Notice the formulas are really the exact same, except one's z equals and one's t equals, and it's strictly based on do you know the standard deviation of the population or not. Other than that, it's the sample mean minus the population mean divided by the standard deviation over root n. That's the same idea as the central limit theorem ideas from the previous chapter. Okay, we're just going to go ahead and find the test statistic here. The claim is that a genetic method increases the probability of having a yellow pea pod. So we don't know anything about the yellow versus green pea pod, so we just assume it's 50-50. The results from the test show that of the 14 pods, 13 of the 14 are yellow. That's p hat, 13 out of 14. N is 14 because there's 14 pea pods. So then I just use the formula from the previous slide, 13/14. I wouldn't round that number too far, so I would just use the fraction if you can. So 13/14 minus p, which is 0.5, divided by the square root. Now the key thing here is don't use p hat. Use the probability or the proportion of the population assumption, which is 0.5 for both p and q then, and then divide by 14 and square root it. Your z-score will be 3.207, etc. Make sure you're able to plug that into your calculator to get that answer. It would probably be a good idea, and we'll show this a little bit later on, to round this to 2 decimal places, because most z-score values we're going to be using our chart from the z-score table, and it will go to 2 decimal places or to the nearest hundredth. For the next one, this says that the claim is that the p pods is equal to 25%, which means p is 25%, the proportion of the population. From my experiment, 152 out of 580, and 580 is n. Same idea though, p hat minus the probability or the proportion of the population, divided by square root p times q, divided by n, and then find that answer. And this z-score value will be 0.671, just to make sure that we're all getting to the right number. But you'll probably round that to the nearest hundredth again to use your table. All right, when we are looking at assessing the test statistic, there's lots of ways that we can do this. And so this is probably a little bit too much information all at once, but we'll be kind of going at this in stages and in chunks as we move forward in Chapter 8. There's going to be an area of rejection region, okay, which is kind of the critical spot that says what's the cutoff, and if you're past that, then you're in the rejection area. If you're not past that, then you're okay. The significance level is denoted by alpha, which is kind of always the leftovers or the outside portion or area to the right with critical values. We're going to assume that alpha is 0.05. So if you don't see anything, and you're like, I don't know if it's important or not, or I don't know what it is, it's always going to be 0.05 unless you're told otherwise. Okay, so that's the probability that it actually would, the test statistic would fall in that region. Okay, fall in the critical region, which is the area kind of outside or in the test statistic area. The critical value is the spot that separates it. Okay, so if the critical value, if you think about going to the doctor and you're at a certain number, if you're past that number, then it's unusual, or it would be considered in this critical area, or it's on the other side and it's probably okay. So you got alpha level. The alpha level we're going to assume is 0.05 unless told otherwise. And then we have these areas of rejection that would cause us to say that the null hypothesis is rejected. The p-value, you have to think probability. The probability value is the probability it's that or anything at least extreme as that. So it's basically like area from that to the end. So if it's a less than, it'd be area of that to the left. If it's greater than, it's area of that to the right. The p-values are found by the area under the curve, which is what your tables show you. We reject the null hypothesis when the p-value is very small. So the probability of the four-digit number, like in the z table, should be less than 5% or 0.05. That correlates directly to what we did earlier in the semester with unusual versus usual. We said kind of 5% was our cutoff. That would be the same reasoning here. The critical regions, if it's a tail to the left, the critical region is the area left of the test statistic. Critical region for area to the right would be to the right. But the critical region in two tails is twice the area on the left or right. So if this area right here is 0.1, then the critical region is 0.2 for that p-value, excuse me. So don't forget, for the two-sided, you may have to multiply something or divide depending on how your table's set up. For z-tables, you're going to have to double it for z-scores. Okay, this goes back to the question we started with. This is the yellow p-pod, so my z-score value is 3.21. But I'm trying to say that it increases something. So that means my null hypothesis is p equals 0.5, but my alternative is p is greater than 0.5, because I'm trying to increase the probability to be higher than 0.5. This is a one-sided test, so I find 3.21, which is right here. It's area to the right, so my p-value is 1 minus the four-digit number in the table at 3.21, which gives me 0.0007 as my final answer. Another option for this is you could find negative 3.21 and just know that it's symmetric, and then it has to be the same answer to the right of 3.21 as to the left of negative 3.21. For the next one, we're trying to show if the percentage of p-pods or the proportion is equal to 0.25, which means my alternative is that it's not equal to 0.25. My z-score was 0.67, but notice here that this is a two-sided test. So while my z-score is 0.67, I have a second z-score of negative 0.67. Really what you should find is just find the negative one. So I found negative 0.67, found the four-digit probability area under the curve, and then just doubled it because I know I have twice as much. Anytime you're using the z-score formula, you have to double that p-value, okay, if it's a two-sided test. Make sure you're able to find that in your z-score table, and don't forget to double it because it's a two-sided test instead of a one-sided test. For critical values, you have to pay attention to the alpha level. So in this case, it says the alpha level is 0.05. We're trying to find what the cutoff is. Find the critical z value for the alternative hypothesis that p is greater than. So since this is a greater than question, it's a one-sided test, so area to the right is 0.05, which means area to the left is 0.95. I look for 0.9500 in the table. I'm trying to find z. Z would correlate to 1.645. That's not surprising. That correlates to a 90% confidence interval, because in a confidence interval, they're always two-sided, and it would be two areas on the left and right adding to be 10%, which correlates to one side being 5%. For the second one, the alpha level is 0.05, but it's a two-sided test because it says the alternative is that p does not equal 0.5. So that means the alternative, you have to split it up. The critical value is always going to be whatever location is area to the right if it's two-sided. If it's area to the left, it could be a negative, so pay attention to that. But the area should be 0.025 to the left and right because together they're 0.05. So you got 0.025 to the left, 0.025 to the right, and then together they equal the 5%. And so the critical value correlates to a 95% confidence interval, which makes sense because a two-sided test is very similar to that, and it's 1.96. The next questions just give you all the information, so later on we'll have to find this information ourselves. It says assume the alpha level is 0.05, the test statistic is 1.01, and we're testing a greater than scenario. That's area to the right, so I find 1.01 in my table, I get the four-digit number, subtract from 1, and I get 0.1562. What this means is this is higher than the 5% or the 0.05 alpha level. This means I'm going to fail to reject the null hypothesis because this p-value has to be less than the alpha level, or less than 5% in this case, or 0.05. Another way to find this answer is to find the critical value. The critical value is the cutoff between the two, so it's 1.645. That's the cutoff. And if you think about it, if here's 1.645, 1.01 is further to the left. It's further in towards this. And so that means my area is even larger, which means I didn't reach the critical region. I'm not past that 1.645. So there's a couple ways that you can go about finding this to make sure that you're still finding if it's a fail to reject or reject situation. Again, this first section, we're just trying to come up with ideas about how to find those things, and that's what you want to use in order to be successful. Your final conclusion should always be reject the null hypothesis or fail to reject the null hypothesis. Then go in to explain what we were trying to prove. For example, if we're trying to prove the majority, we'd say we reject the null hypothesis, there is sufficient evidence to support some claim that it's actually a majority, or fail to reject and we don't have the evidence to support the claim. Those are the wordings that we're going to be looking at. We'll deal with that more in sections 3 and 4 as we move forward in this chapter. Again, that's a lot of information that we're looking at with null hypothesis and alternative. You want to make sure that you're coming up with a conclusion based upon the p-value or the critical value. And my suggestion is you kind of write how to find p-values, how to find critical values, and use your table and your z-score and t-table charts, which we'll deal with more once we get into the mean questions with the t-table. Have a good day, everyone.